All right, in this video we are going to talk about exponential functions. The two learning targets are I can evaluate exponential functions and I can identify and graph exponential functions. So getting started, exponential functions can be used to model population of an insect. So for example, let's say someone was taking some data and wanted to know about an insect population. They started collecting the data on day 0, right? That's the first day that they collected data, and they saw that there were 2 of that insect, okay? And they went back the next day, so that would be 1 day after they started collecting data, they saw there were 6. 2 days after they started collecting data, they saw that there were 18. 3 days, there were 54, okay? And then they saw that the common ratio between that is multiplying by 3. And then over here, we've got this graph, okay? It looks like this, all right? If I were to connect these, kind of looks something like that, all right? So that's kind of the idea of what an exponential graph is going to look like. It's going to increase, kind of like the geometric sequences that we were just working with, okay? So if I took this table and this graph and I wrote an equation, okay, this equation, this function rule, f of x equals 2 times 3 to the power of x would describe the pattern, okay? Notice 2 is the starting population, right? Started at 2. And 3 is the amount by which the population multiplied each day, right? We multiplied by 3. And then x in the exponent represents the time in days for this specific example, right? We've got our x-axis representing time, okay? So this is what exponential functions look like. Now, they're very similar to the geometric sequences function rules that we wrote yesterday, but they are definitely different. So exponential functions, f of x equals a times r to the x. And I've got a couple restrictions. So the first one is that a cannot equal 0. The second one is that r cannot equal 1. And the third one is that r must be greater than 0. Okay? So for exponential functions, a represents the starting point. So like in the last example, it was the first population of the insect, and r represents our constant ratio, right? Or our common ratio, like when we talked about geometric sequences. So we're going to compare the 3 types of functions that we have done so far this school year, okay? So we started off talking about linear functions. And we did y equals mx plus b, where m is my slope and b is my y-intercept, okay? Linear equations in their graphs are graphs of straight lines, right? It's going to be a straight increase or it's going to be a straight decrease, something like that, a straight line, a constant change, all right? Quadratics, we just finished talking about quadratics for so long. Quadratics would be ax squared plus bx plus c, okay, right? C was my y-intercept again. A told me the concavity was the concave up or concave down, and then we could calculate a lot of other stuff like the axis of symmetry and other things like that, okay? Quadratic graphs look like this. They look like that, right? Or they could be going down, depending on the concavity. Okay? Lastly, the one we're going to talk about for all of Unit 11 is exponential functions, okay? Exponential functions are really interesting. I've got x in the exponent, so that you think exponential, x is in the exponent. And graphs are going to look different. We may see some graphs like this. Okay, we could see some graphs like this, and a lot of other different shapes, okay? But they kind of look like, I don't know, I described it as like an elbow almost, like a little bit of a rounded elbow. That's what exponential graphs are going to look like. And we may have ones, I guess, too, that would look like that. There's lots of different types of exponential functions. So let's look at a specific example. It says the equation f of x equals 2 times 3 to the x models an insect population after x days. This is the first example that we started with. Let's make a table. So I've got x, and I'm going to evaluate f of x at different functions, or at different days, for different days, okay? So I'm going to start with 0, which means I'm going to do 2 times 3 to the power of 0. If we want to type it into our calculator, 2 times 3 to the power of 0, and we get 2. Okay, and we do day 1, I'd be 2 times 3 to the first power. 3 to the first power is 3, 2 times 3 is 6. Okay, then day 2 would be 2 times 3 to the second power. 3 squared is 9, times 2 is 18. Okay, and I do 3, 2 times 3 to the third. And we could keep going and going and going, right? 2 times 3 to the third would get me 54. Okay? So if I wanted to find the population after 7 years, okay, I could keep going and filling out the table and do 4, 5, right, and keep going, or 7 years in this case represents my x. So when x equals 7 years, what would be my output? So if I use function notation, I'm going to find f of 7 equals 2 times 3 to the 7th power. And I'm going to plug that in to my calculator. 2 times 3 to the 7th power. And I get 4,374. Okay, and that would be the insect population after 7 years. Okay? So, just like we talked about, exponential functions have a common ratio. Okay, ratio is something that we are multiplying by, right? We're multiplying by 3 in each case. Okay? If it does not have a common ratio, then it is not an exponential function. It may be linear, it may be quadratic. So now we're going to have to be able to tell if something is an exponential function. So let's take these ordered pairs and let's put them into a table, because tables kind of help us visualize. So the first point is -1, 1.5. The next point is 0, 3. The next point is 1, 6. And then I've got 2, 12. Okay? So in order for it to be exponential, it must have a constant ratio. So now if I look at my x's, I'm adding 1. And what's happening within my y values? Okay, so we can find the constant ratio the same way we found the constant ratio for our geometric sequences, is if we divide backwards and we can see if it's consistent. So 12 divided by 6 is 2. Okay, then I keep going. 6 divided by 3 is 2. And 3 divided by 1.5 is 2. So that means for every increase in y, x is being multiplied by 2. Is that a constant ratio? Yes. It must be exponential because it has a constant ratio. Okay, you could have gone from x to x in the list, and then from y to y in your list, but it is nice to kind of rewrite it as a table and see that clearly. So if I've got another example, let's put this into a table. Got -1, 1, 0, 0, 1, 1, and 2, 4. X is adding 1. And what's happening to y? Okay. Well, one thing I see that's happening, in order to get from 1 to 0, I have to multiply by 0. but I'm not multiplying by 0 to get to the next one. Okay, let's use what we know from geometric sequences to calculate that common ratio. I do 4 divided by 1, I get 4. So it should be 4 throughout the rest of the y values if it's exponential. So if I do 1 divided by 0, wait, I get undefined. So that means that there is no common ratio, so it is not exponential. Okay, so now let's get to graphing exponential functions. Let's graph exponential functions. So I've got 3 times 4 to the x. I'm going to find an x value, and I'm going to evaluate y. Okay, let's start with 0 to give ourselves kind of a reference. So we'll plug in 3 times 4 to the 0. Anything to the 0 power is 1. So 3 times 1 is going to give me 3. Okay, so 0, 3. I'm just going to estimate it in there. It doesn't have to be perfect. Okay. Next, I'll plug in 1. So 3 times 4 to the first. 4 to the first is 4, and 3 times 4 is 12. Okay, so if 10 is there, we'll just estimate 12 is right there. I plug in 3. I'm going to do 3. Oops, I missed 2. Plug in 2. 3 times 4 squared. I can type this one into my calculator. 3 times 4 squared is 48. Okay, so 2, I'm going to be way up there. Okay, if I were to do 3, I'm going to be way up off the graph. Okay, if I plugged in 3, I would do 3 times 4 to the third, and I get 192. That's going to be off the graph. Okay, so we know that from that first point I started with, it's going to kind of curve upward. Okay, and it's going to go up really fast. But what's going to happen when I go the other way? Is it just going to go straight down, or what? We can do that by plugging in these values, -1, into our calculator and kind of seeing what happens. So if I did 3 times 4 to the power of -1, I get 0.75. All right, well, that would be even closer. Now if I take that and I do that to the -2, I get 0.1875. Okay, well, that's even closer to 0. I do that to the -3, and it's even closer to 0. Okay, is it ever going to get below 0? Well, let's look way in the future. If I plug in like -50, if I said -50 is my x value, okay, what that reads, oh, that's so big. It's so small, but I don't know if you know how to read scientific notation. So let's do one that's a little bit not as small. Oh, it's still really small. Anyways, when I see something like that, e to the -30, that means times 10 to the -30 power, which means I need to move my decimal 30 places to the left. So think about that. 0.000000000000000000000 29 zeros, 2. That is tiny, 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 tiny. But it is not negative. So what happens with exponential functions in this case is it will keep getting closer and closer to 0, but it will never reach. And it will end up giving us some kind of elbowy curvy that looks like that. Okay? So let's do one with this decimal. I've got 4 times 0.6. And I'm going to plug in values for x. And I'm going to see what this one looks like. Or should we try negative 1? Let's try the negative 1. Let's try the negative 1 and see what this looks like. Okay? So x and then y equals negative 1/4 times 2 to the x. Okay, we'll start in by plugging 0. So we get negative 1/4 times 2 to the 0. Well, anything to the 0 is 1, so that's going to be negative 1/4, which is also 0.25. Okay, so that's like, if that was half, it'd be like right there. Okay? When I plug in 1, I want to see what happens. Okay? So, when I plug these in, I need to make sure I put negative 1/4 in parentheses. And I want to multiply that by 2 to the power of 1. And I get negative 0.5. Okay, so that's right here. Okay. What about 2? I plug in 2, negative 1/4 times 2 to the power of 2. And I get negative 1. So I'm going to plot that. And I keep going, plugging in 3. Negative 1/4 times 2 to the 3rd. And I get negative 2. Okay, I'm just going to keep going so we can kind of get a picture. I can see it looks like it's going to be falling right there. If I plug in 4, let's see what happens. Negative 1/4 times 2 to the 4th is negative 4. Okay, so now I can see kind of where it's going. So if I can see that little curve right here, it's going to go down. In order for it to follow the pattern of an exponential function, it's going to have to kind of go like that this time. So let's check to make sure that it's going to keep approaching and approaching 0, but not go above 0. So if I plug in negative 1/4 times 2 to the negative 2, what do we get? Negative 0.0625. Okay? If I take that and I multiply it by negative 3, okay, getting closer and closer to 0, but not reaching it. If I change that to negative 8, right? Again, e to the negative 4th means times 10 to the negative 4th. Okay, so let me kind of demonstrate that. It's 9.7 times e to the negative 4th. That's the same thing as 9.7 times 10 to the negative 4th power. So I take 9.7 and I move the decimal place 1, 2, 3, 4, and I get 1, 2, 3, 9, 7. Okay? That's how scientific notation works. That's a small number. I think that was supposed to be negative. And it's still not over 0. Okay? So that's my 2 examples of exponential functions. You just need to be plugging in values to kind of get an idea of what it's going to look like. Then you can use your calculator to plug in some more values to see where it's going to keep getting closer and closer to, but never touching.